Okay, so we're going to look at some calculations we can do with electrolysis and electrolytic cells. So at the beginning of electrochemistry, we learned about Voltaic or Galvanic cells. Those are the cells that form the basis of a battery. So in these Voltaic or Galvanic cells, we're using a redox reaction to produce an electric current. And the way we do that is we take the redox reaction and separate the oxidation and reduction half reactions into separate compartments and then connect them together with a wire and the salt bridge. And then when we connect everything together, the reaction starts, the oxidation occurs and supplies electrons to the reduction side where reduction occurs. So as long as everything's connected together, that reaction takes place once I connect everything, so that we call that a spontaneous or thermodynamically favored reaction. In an electrolytic cell, what we're doing is we're causing a reaction to occur using electricity. So if we put the parts in an electrolytic cell together, the reaction we want will not happen. That is called a non-spontaneous reaction. So we have to force that reaction to take place, and we do that with an external source of electricity. So in electrolysis reactions, we force the reaction to take place by applying electricity to the reaction. And that causes the non-spontaneous or non-thermodynamically favored reaction to take place. So if we want to quantify this, the most common application you will probably run into is called electroplating, where we take a metal, like something that's gold-plated or silver-plated, we take a metal and coat it out over another metal. That is an electrolysis reaction, where we take some aqueous solution of, say, silver ions and force them to become silver metal by using electricity. So we can put some numbers to that. How much silver wood plate can I get to plate out on something? How long will it take to plate a certain amount of silver out on something? We can do those calculations, but they require some numbers. So the numbers, here they are. Here are the basic conversion factors we're going to need. We start with a coulomb. Coulomb is a unit of charge. One electron has a charge of negative 1.602 times 10 to the negative 19th coulombs. So we don't really ever do much with one electron, so we really deal with moles. So 1 mole of electrons, just using the math, would have a charge of 96,485 coulombs. This number is referred to as Faraday's constant, capital F. So Faraday's constant is actually a conversion factor, 96,485 coulombs in 1 second. This is on your formula sheet, so you do not have to remember that number. The other conversion factor we need to deal with is something called current, electric current. It is expressed in amps. You may have heard this term before. So amperes or amps is the rate of flow of electric charge. So you'll notice the units of amperage are coulombs per second. So 1 amp is 1 coulomb per second. So we can use these two conversion factors to do some math with electroplating. So we'll go ahead and work through one example of this. There are many variations of it, but we can do one basic example of an electrolysis reaction. So we're going to gold plate something. So I have some gold ions, which I'm going to convert back to solid gold and take the mass of the solid gold. So in electrolysis reactions, one of the things that's a little bit different than a regular, say, stoichiometry problem is that we really only worry about the reduction half reaction, or one of the half reactions. Typically it's the reduction half reaction. So in this case, the only thing we're worried about is the fact that it takes 3 electrons to change one ion of gold 3 plus to solid gold, or 3 moles of electrons to change 1 mole of gold ions to 1 mole of solid gold. So it's not really a full chemical reaction, it's a reduction half reaction, but we can still use that information. So if I want to get to my question, what mass of gold will be deposited in 1 hour if I use a current of 1.5 amps, the first thing I need to realize is 1.5 amps is the same as 1.5 coulombs per second. So that is a conversion factor. I notice the only other number I have in this question is 1 hour, so that's my beginning point. So I know I'm running this reaction for an hour. So I can figure out, the first thing I can figure out is how much charge flows through there in 1 hour. So I know that I have 1.5 coulombs per second, but I also need to convert hours to seconds because this is hours, this is in seconds. So I know there are 3,600 seconds in 1 hour. So now I can figure out how much charge that would be by taking my current and saying, well, in 1 second, I get 1.5 coulombs. So now I know how much charge flowed through my cell in 1 hour. So how do I get this to something where I can work with my reduction half reaction? Well, using Faraday's constant, I can change this amount of current into a number of moles of electrons, because I know 1 mole of electrons is 96,485 coulombs of charge. So now I have how many moles of electrons actually flowed through my cell. So now I can go up to my half reaction and I notice that it takes 3 moles of electrons to produce 1 mole of solid gold. That's what this half reaction says. So 3 moles of electrons give me 1 mole of gold. And I know 1 mole of gold is not 196.97 grams of gold. So I have taken time and converted it to grams of gold using dimensional analysis. So if I do the calculation, I end up with 3.67 grams of gold. So that's how many grams of gold would be deposited in 1 hour from my solution if I have a current of 1.5 amps.